Welcome to the Energy Central Power Perspectives podcast. This is the podcast that brings leading minds from the energy industry to discuss the challenges and trends that are transforming and modernizing our energy system. And a quick thank you to West Monroe, our sponsor of today's show. Now, let's talk energy. I'm Jason Price, Energy Central podcast host and director with West Monroe, and coming to you from New York City. With me, as always, from Orlando, Florida, is Energy Central producer and community manager Matt Chester. Matt, we have with us today a leading voice on the future of vehicle electrification when it comes to preparing the U.S. utility industry. EVs and the overall electrification of our mobility system is a frequent topic for us on this podcast, but we're going to take it to a new direction. But before we dig in with our guest, Matt, can you recap for our listeners some of the episodes of the podcast that may be worth revisiting after today's show?
Sure, Jason. I'm always happy to give recommendations on past episodes of our show for people to listen to. And in fact, we recently put together a playlist of our electric vehicle tied episodes, which you can find on our SoundCloud page called Driving the Future, EVs and the Utilities. I'll also put a link to this playlist in the show notes of today's episode. But if you go there, you'll find some of our great previous episodes like Esri's Bill Meehan and Pat Hold debating the utility role in transportation electrification, Lauren Youngdahl Snyder of Consumers Energy talking about what their utility is doing in preparation for the EV shift, Will Ellis of Pepco highlighting how the EV rollout should be conscious of equity. And that's just the beginning. So otherwise, plug people back into that playlist to hear more.
Thanks for that, Matt. No doubt today's discussion will fit right in with the rest because we're being joined by a leading researcher on this topic. Specifically, we have the privilege to welcome Timothy Pennington, who serves as research group lead in vehicle electrification at the Idaho National Laboratory. Timothy and his team are focused on vehicle grid integration topics such as energy management, cyber and physical security, and wireless charging. His group studies what the grid infrastructure must look like in order to support the electric transportation future that we all know is coming. And his group either coined or popularized many of the terms we use today in EV transformation. I know we can chat for hours on this topic, but we only have Tim for a limited amount of time. So let's go ahead and bring him in. Tim Pennington, welcome to the Energy Central Power Perspectives podcast.
Thanks so much for having me, Jason. I'm really excited to talk with you today about transportation electrification and share with your listeners a bit about the research that we've been doing here at Idaho National Laboratory on grid integration of electric vehicles.
Well, we're thrilled to have you. So, Tim, before we dig into the topic, tell us about INL and the research group you're leading.
INL is one of 17 Department of Energy national laboratories, and INL is known as the leading nuclear energy laboratory with 4 operating nuclear reactors. We're located on a desert site here in southeast Idaho of 890 square miles of U.S. government land. We have 5,400 employees and growing rapidly. My department is known as the Energy Storage and Electric Transportation Department, and we work across what we think of as a spectrum from the molecular level of new chemistry for batteries all the way through to the macro system level of the transportation system and the electric grid. And we're thinking not only about what's happening today by studying new entrants to the market, but also what the future holds with new batteries and even the long range thinking about disruptors to the transportation market that include things like vertical takeoff and landing vehicles, drone package delivery, and how those might impact the energy system as well. My research group within that department is specifically focused on electric vehicle grid integration, VGI we call it. This includes all the ways that electric vehicles do and will change how they interact with the grid. I say interact, not just impact, because I think there are possibilities of both positive and negative effects, and we need to understand those and then work to find as many of the positives as we can, mitigate and prepare for the negative. Specifically, our group actively runs projects and focuses our research into the 3 areas that you mentioned up above: EV charging intelligence, that simulation of the impact, knowing what's coming from EV charging, how can we control that, how might we incentivize individuals and organizations to charge in ways that are more beneficial and thus achieve energy management. Cyber physical security, so there we're studying the impacts that could happen on the grid in a worst day kind of scenario while. We work to find the vulnerabilities in the EV chargers, the networks that support the chargers, the vehicles, detect those, prevent them where they can be prevented, mitigate them when things are occurring that we've not yet prepared prevention for, and continue to provide maximum transportation energy delivery. And our third area of focus for my team is wireless charging. So that is both static charging, and that focuses in interoperability primarily, as well as dynamic or in-roadway charging. And there we're looking at the safety, the integration, and facilitating a lot of detailed laboratory testing and field testing of new wireless systems.
That's pretty comprehensive, and we'll dig into some of that. So no doubt people listening understand to some degree the challenges EV presents to the grid, but perhaps you can paint a picture on this and the cost challenges we face.
Years ago, INL was working on some research as the newest high-powered charging stations came online. These are what we call extreme fast chargers. They're generally in a category from about 75 or 100 kilowatts all the way up towards 400 kilowatts. And this is what you see when you're in a big box store parking lot and there's a group of 6 chargers on a major national network of chargers. And we started looking at the power requirement for these and what they might be able to draw in a future where vehicles are prepared to charge at that power, and thus what the utilities might be doing to interconnect those. And so we did some investigation, checked out the stations around us, also the equipment that we have actively been adding to our laboratory. And if you take 6 of those, and the most common are at 350 kilowatts, you could have 2.1 megawatts of nameplate capacity at this charging station. For listeners like myself who are newer into the electricity market world, 2.1 megawatts is a huge amount of power. We compare that to our local regional hospitals that have transformers in the 2 megawatt range. But an electric vehicle charging station will never operate like a hospital. It will have these ramping events that go from 0 to 100% of its possible power draw in maybe a 15-minute time period and then scale back again. So those could represent demand charges to the utility's customer of upwards of $30,000 per month, while the energy charge might only be $3,000. And we've heard that. Electrify America is quoted as saying that 80% of their utility bill is their demand charge, not their delivered energy. So that's a real challenge to the businesses trying to operate charging stations, but also to the utilities that are trying to effectively and appropriately connect these types of loads onto their existing system. I use this example at 6 chargers because it's something we're seeing today. It's something we're hearing lots of people talk about as they look at new stations. But in California, we see Tesla installing this similar type of equipment with 50 or more chargers at a single location, which is, a mind-boggling amount of intermittent power at a very new, small footprint location. On top of that, or building on that, listeners may have heard about the NEVI program, the National Electric Vehicle Infrastructure Program, funded out of the Bipartisan Infrastructure Law. It has $5 billion over 5 years to build these types of extreme fast charging stations all along major highway corridors across our nation, all 50 states and 2 territories. Some of these corridors do not have immediate access to 3-phase distribution power. Others will have substations that are already at capacity. We're hearing from utilities that they're finding 18 to 24-month lead time on some transformers and other power equipment when they go to add more capacity for these types of stations. So that's a real challenge that needs to be addressed by both industry, and we're hoping to help by adding some of the knowledge we've been gaining through our research on these topics.
Yeah, absolutely. We've been hearing a lot about the need for more transformers. The manufacturing side has been, due to supply chain and other factors, the war in Ukraine and the like, just creating a bit of a bottleneck in the availability of transformers to help support this growth you're describing. So let's dig in the specific areas that you and your team are aiming to address.
So a little bit of background about my team specifically, which substantially predates me. But for years, decades really, INL has been studying the charging behavior and the operating performance of electric vehicles, starting by instrumenting and testing emerging electric vehicles from major automakers that were coming to the market our work was starting in early 90s, years before GM put its EV1 into production in 1996. So we've been testing physical hardware with instrumentation, collecting that data. We then led a study that was known as the EV project and collected data on over 8,000 vehicles, 7,000 chargers, 17 different regions across the country, and recorded 124 million electric miles driven by those early EVs. From all of that data, we began running lots of analysis, as National Lab researchers will, to gain insight. We then realized that in addition to analyzing the raw data, we could build models of what those electric vehicles looked like as they charged. That eventually evolved into a full agent-based modeling simulation platform that we call Caldera. And with that, we can represent millions of vehicles as dynamic loads moving around the transportation network and connecting to and charging from the electric grid. We've recently taken that Caldera tool and launched it open source. We're actively working as researchers on making that code more usable to individuals. It has largely been a research tool used by those who created it. So we have some effort to improve the open source code, but also, and I'll speak about it in later, I think, as we talk about the reason for it, but we're taking that same tool and building a public-facing web-based tool for anyone to use, regardless of their knowledge of computer software. So we represent those loads in our Caldera simulation as dynamic. And I say that specifically because above level 2, which is your residential or workplace 7 kilowatt charging, above that, vehicles have a charge profile. So that means they're not drawing 7 kilowatts constantly for the 6-8 hours that they need to charge in their garage, but rather the profile takes on a unique shape for each vehicle and the charger that they're connected to, ramping up to their full power. Today, that maximum power in the Porsche Taycan is somewhere in the 260, 270 kilowatt range, holding that power for only just a few minutes and then beginning to follow a ramp down curve. Each vehicle has a unique shape in that profile, and each manufacturer is actively developing that profile through their battery management system, all with the goal of delivering as much charge energy as possible so the vehicle can achieve more miles more quickly, but also protecting the health of the battery. So constant trade-off, the different chemistries require this level of management of that charging process. It's really important to understand that, and this is what we found and part of why we built the simulation, because those 6 chargers that I was describing before, it's extremely unlikely that you would have 6 Porsche Taycans pull in all at 5% state of charge in their battery and then plug in instantaneously so that they would achieve that peak charging power at the same time. Highly unlikely. So assuming that they miss each other by even just a few minutes, each station will never peak out at the 1.6 megawatts today's best, fastest vehicle could charge at, never mind the 2.1 megawatt nameplate capacity of the chargers that are at the station. However, what I just told you, it has to be proven and validated before utility grid planners or PUC type regulators are able to use that information to justify decisions that they make in providing service.
It's really interesting. So when it comes to EV charging intelligence, it seems like the goal is to be more nuanced, identifying peak timing and strategies for charging rather than using the blunt force tool of overbuilding generation and transmission, which is really what you're aiming at. So let's dive more into this. What exactly is EV charging intelligence, and how do we get there from the business as usual today?
As I was just speaking about, it's very important to understand the charge profile of each individual vehicle. This is influenced by its technology, but also by that state of charge at which the vehicle starts its event at. So how low is it when the driver decides to connect? But other factors go into it. The ambient temperature, the battery condition. Have you been driving before, or have you been parked and had the vehicle totally off? The rating and the condition of the DC fast charger. Has it been used by a bunch of vehicles right before? Is it the fastest charger on the market, 400 kilowatts, or a slightly lower 250 kilowatt supercharger? All of those go into what the charge profile is going to look like. And our software works to mate those two units up, the vehicle and the charger, and determine that profile. So then once we have a vehicle profile, we've also got to determine when each vehicle will arrive wanting a charge and how much charge it's going to for. We run that all through simulation, and from that we can build a baseline or what we call an uncontrolled charging scenario. This is really load forecasting of a possible future scenario at a specific location where we know vehicles are moving around and where we hypothesize there could be a charging station. And that allows us to look at those types of impacts, but quickly it becomes apparent that there are peaks and there are valleys, and that we would like to, shift some of that energy demand to other times, shaving those peaks, filling those valleys, and thus smoothing out the aggregated demand on the system. So our simulation platform, Caldera, allows us to test out various types of controls on this charging. So we can have stationary batteries at the charging station, which are used in an arbitrage fashion to place a ceiling or a cap on the grid, or the stations draw from the grid while providing additional energy from the stored battery and then recharging itself after the cars have gone. You have a longer period of time where the station is drawing energy, but at a lower peak power. We've also investigated and built into the simulation a reservation system that we don't believe exists in the market yet today, where vehicles can schedule their charging on available ports at specific charging stations and possibly receiving a dynamic price offer for their different possible reservation time and location. Or there could be other incentives provided to reserve charging at ideal times. We have looked at dynamic pricing alone. We can forego the reservation system, but have vehicles moving around viewing, as we do today at gas stations, the price up on a big signboard and making our decisions about, am I going to charge now at this station, or can I keep going? We've also worked some with industry. We believe they are bringing tools to market that I think of like a circuit breaker, a CE certified device which limits the grid power. Even if that nameplate capacity is 2.1 megawatts, someone makes a decision they're going to install this industrial certified equipment that limits them at 1.5 megawatt. And then the same device will manage the individual chargers through a power sharing regime, possibly including a battery, but possibly just doing sharing of energy across the vehicles that arrive, which we already see the early leaders in the market put 2 ports on a single charger. They called it a 250 kilowatt charger, but if 2 vehicles plugged in at the same time, each one only got 125 kilowatts. And so positives and negatives to that, drawbacks in customer satisfaction when they realize what's happening. We've also seen industry working on other controls for that same type of circuit breaker power limiter that would do a first in, first out. So each car as it arrives is getting maximum energy. When another car arrives, it gets whatever energy is available until that charge profile ramps down the first car. And now the second car can start to ramp up as power is available, or other sorts of schemes. So we see these as ways that we can really work on energy management and provide some insight to what's needed for the industry.
Pretty comprehensive, and these are very real and practical issues that we're facing, especially with the proliferation of EVs. You only need to get this addressed even more quickly than even, say, last year. So you're really on the cutting edge here, Tim. Let me ask you, so much of your effort is centered around the modeling of EV charging needs and building your models and modeling software and using that to inform next steps. So how do you get stakeholders across the industry to end up utilizing the outputs of this work and the work coming from your team?
Yeah. One of the things I mentioned earlier in our talk was about an effort we have going right now to take our Caldera software and make it available to everyone. So we've done that through open sourcing the source code. But one of our largest efforts right now is squarely focused on this deployment and assistance to industry. It's creating a version of our simulation. We're calling it Caldera CAT. It's supported by the Joint Office of Energy and Transportation. That's a new office between DOE and DOT, created by the Bipartisan Infrastructure Law. That's the office responsible for the NEVI program. So Caldera CAT is designed to assist the NEVI program as a publicly available web tool, specifically for forecasting power demand at NEVI compliant stations along any of the designated corridors. Our hope is that this tool will be used by potential station operators as they analyze where to put their charging station and as they submit their service requests to the utility, and then it could be used by utilities to evaluate what the appropriate service level is for the proposed station. And it can also be used, and we're looking at other ways to improve and customize it for PUC type regulators looking for an independent third-party assessment of how much load will be needed to serve at an individual location to ensure that distribution upgrade costs are well spent. We hear all the time from utilities, our make-ready programs are sometimes accused of gold plating. We're putting out infrastructure where we don't yet know that vehicles will be. We can't justify the load. So we're working to fill that space by being a truly independent, federally funded tool for forecasting those loads. In your question, about how do we get our research out to market and make a difference, we trust that our work on controls, those mitigations and energy intelligence methods I mentioned up above, as well as the information we've found in grid impacts and how we might mitigate those. We publish those in journals. We go to conferences. We actively work on multiple industry groups. The U.S. Drive Consortium, DOE is now running a grid assist program specifically for utilities to gain information from the national labs. And working with the Joint Office, we're often publishing our papers into their resources pages. So I would encourage utilities especially to look at those resources or reach out to the Department of Energy and find additional resources from the national lab where they can learn about these technologies we're exploring, how they might help, and what needs to be developed further by industry in those spaces. Additionally, we've seen and we've spoken with several startups who are working as what we call third-party aggregators. So they're selling control services, especially in the level 2 space right now, but I think we'll see that progress as there is more and more fast charging, and it will need different types of aggregation. But today, there are startups who will work with individual EV owners at their garage to have a Wi-Fi connected remote charger. They provide an incentive of some sort to the EV driver to share control of that charger, and then they aggregate thousands of those controllable chargers to present a controllable load that the utility can then incentivize by working with the aggregator. So how they automate those systems and what types of controls they're using are things that we've been studying for years and years, and we're happy to share through our literature. We also see battery system providers specifically marketing tools, batteries, and control systems that are intended for co-location at fast charging stations. How they will control those, what the architecture of the battery system is, what chemistry of a battery is most efficient for that application are all things we've studied and published about.
Yeah, that's great. So on Energy Central, we have a broad, representation of the utility space. So we have co-ops, representatives from co-ops, munis, IOUs, power institutions, and so on. So, share with us what's it like interacting with them, because every utility has its own needs, especially with the EV transformation. So maybe you could describe to us what are the differences in the types and size of utilities and how you're approaching this and how you're working with them as they approach these issues.
Yeah, absolutely. We have worked with utilities of all sizes. You're 100% right that size, type, and also the location of a utility really determine how they're approaching the EV transition, transportation electrification as a whole, and how far they are along in that transition. When I mention our partnership on existing projects, those are often with IOUs who are larger, well-funded, may have their own dedicated EV team who has been reading our research and now wants to partner and roll out a pilot project. Those have been great partnerships. We've learned a lot. We hope we've shared and they've learned a lot. But especially now under the NEVI program and with the funding from the Joint Office of Energy and Transportation, we've been able to focus on providing some tools that will be really useful to the munis and the co-ops who, for the most part, have not had EV teams. There are exceptions to that. We've worked with some great partners like SMUD, the Sacramento Municipal Utility District, who is absolute leader in the EV space and the DER and energy storage space, and their EV team's been great. But when I talk to, say, my local co-op, the Fall River Electric Co-op here in rural mountainous eastern Idaho, they don't have an EV team. When I call, I get the chief engineer on the phone, and she likes to talk about what are we doing for electric vehicle infrastructure. They're installing some of their own company-owned fast chargers on town property. So everyone's approaching this, but they're all different. And for the smaller groups, that's a large focus of how we're rolling out the Caldera Cast web tool. We want to make sure that that tool is really simple to use in its basic form for someone who's never even sat in an electric vehicle, let alone held an EV charging cable. We want them to be able to type in a location of a charging station, how many chargers they want to put in, and get some level of a forecast. So we're pulling traffic data, registered EV data, predictions of what adoption rates are going to be in this area over time. How close is it to a major transportation corridor where non-locals will be charging? And we can produce a load forecast from that for folks. We also are working to add to that levels of sophistication, I'll say, where you can drop down and say, well, I don't like that adoption rate forecast that you've pulled from the literature. I want to use a more extreme adoption rate where 80% of vehicles are electric by 2045, and see how that's going to load this individual charging station so that I can right size my charger. We've also seen or heard, we've been talking to utilities through a lot of stakeholder engagement outreach programs, holding our own webinars and listening sessions. We've heard from utilities that they are already overwhelmed by new service requests and analyzing those interconnections. And we know that an electric vehicle charging provider, so whether that's an individual charge network provider, I talk about them as, those are your national networks that are putting charging stations all across the country, or whether it's local municipality who knows they want to put EV charging somewhere in their region, they don't necessarily know where to put it, and they don't know what the electrical infrastructure is that will support it. So if I know I want to put a charger, a NEVI compliant charging station somewhere between exit 310 and 320, because that's what's needed for the NEVI program, that's where I see the traffic is. Well, I may not know that putting it at exit 312 is going to require an entirely new substation built and drawn off of the nearest transmission line, stepped down to three-phase 480, brought into my transformers, and cost a whole lot. But if I went to just station or exit 314 to build my station, I land on a different distribution feeder. That circuit has lots of capacity, and all I need are those transformers. The only way in many areas for a developer to try to assess that is to put in multiple service requests, which is going to further overload these small utilities who don't have streamlined processes or staff capacity to analyze all of these. So we're working on our Caldera Cast to forecast what the load might be, and we're in a partnership with the Pacific Northwest National Laboratory to create another public-facing tool that utilities can use to show their capacity, especially along NEVI corridors, without needing to disclose what they consider proprietary information of their actual circuit maps and distribution lines. So those are some ways we're really trying to support utilities of all sizes, and regions can be very different, even without traveling all that far. We look at California, which has the greatest number of EVs today, huge stations being deployed, lots of government support, utility support for make-ready programs to get ahead of it. And you go just 2 or 3 states through to places like Wyoming, and they have on the order of hundreds of electric vehicles registered in the entire state. They have expanses of highway that don't even exits with any level of infrastructure every 50 miles where the NEVI stations are intended to be installed. And so we're working to support them as well. Their adoption will be different. Maybe it's because most folks in Wyoming drive trucks and we don't have a whole lot of EV trucks on the market. But I think that'll shift too. I think it's coming all across the country at different rates.
Yeah, absolutely. Unique and fascinating, to say the least. I do want to bring up a fascinating topic that you shared with us in the planning session before this recording. You had mentioned some innovations in wireless charging. Could you tease out for us a bit of what that looks like and how INL is looking to develop this, I think, intriguing technology?
Yeah, absolutely. I find it fascinating as well. Wireless charging for anything really is an amazing convenience, right? It doesn't seem like all that big a deal, but not having to plug your phone in, simply being able to set it down in the right part of your desk as you're working and it magically recharges is fantastic. It really enables what we call opportunity charging. So as we bring that same technology up in power level and develop it for electric vehicles, it can make a big difference. When I talk about vehicles being controlled as a resource for the grid, either consuming when it's most desirable or a bidirectional future, it requires that those vehicle assets be connected to the grid. There are lots of people who don't plug in their EV in their garage every night because they don't need to. That's kind of little known. We all drive less than we think. Our batteries in today's EVs are bigger than they need to be. And so the majority of the time, folks can get by charging maybe just a couple nights a week. But if they're not plugging in, they're not an asset to the grid. So wireless could really make that possible, where wherever you park at night, there's a charging pad. You don't do anything. Your vehicle is connected. It can always top up. It can always be a resource. What we need to do there is have standardization and interoperability to make that possible. So like the QI or QI standard for phones that allows us to connect most phones to most wireless chargers, we're working on that for electric vehicles. And then within even the standard, the implementation is really important. All the manufacturers will need to ensure that their vehicle and their charger on the ground are able to talk to one another, or it's not useful. It's only charging in your garage rather than every time you go to work or the shopping mall and you park over a charger. So INO has worked in that space for many years on interoperability. The next and really fascinating part of wireless is to move to dynamic wireless charging or in roadway wireless charging. So in my opinion, this is successful if we take those same stationary chargers and we're able to use them in the roadway. So this means not only when you're parked in your garage, but when you're driving in a certain lane on the highway, you're able to gain power while in motion over that section of road. More convenient, you're getting charging when you otherwise weren't. You don't have to do anything to achieve that. But there are also potential battery size reductions. So if I know the only reason I have such a big battery pack is for the great American road trip that I take once a decade, if I can drive on highways that are electrified, I can still have a much smaller battery that achieves my needs on daily driving and non-electrified space and recharge it as I'm driving down the road to get much greater ranges that we need for those road trips. We're headed to an industry test track this summer up in Detroit, where along with two other national labs, we're testing out a 200 kilowatt system installed on the bottom of a real production EV, and we're going to charge it while we're driving 45 miles an hour around the test track. Super exciting.
Yeah, that's great. Really interesting. And this has been an enlightening conversation. And we're going to give you the last word, Tim. But before we do that, we have something called the lightning round, which is where we ask you a set of questions and you are to give the response either a one word or phrase. And this is an opportunity for us to get to know you more, the person rather than the professional. So, Tim, are you ready?
I am. Fire away.
Okay. What was your first car and what is your next car?
My first car, age 16, was a Mitsubishi Eclipse with a manual transmission. Next car, I need all-wheel drive. I'm very torn between a battery electric or a plug-in hybrid electric vehicle. Perhaps it might be a VW ID4, a very interesting model recently to market, but I'm waiting to see if they open up orders for a lower cost trim package with the all-wheel drive.
All right. Latest book, TV, or movie you may have recently consumed and would recommend?
Sure. Outside of all the research journals that I read at work, most of my reading is done with my 6 and 7-year-old children. That said, it's not all Dr. Seuss. We've recently moved into some novels, and I'd highly recommend a new series called the National Park Mystery Series by Aaron Johnson. Anyone with kids will love reading it themselves and watching their kids get into it.
That sounds good. I'll put that on my list. Who are you inviting to your dream dinner party? Major celebrities or historical figures?
So now you're digging into some of my non-national lab, non-EV histories. Some of my idols include Jacques Cousteau, leading oceanographer, really created the first scuba system. I'd also invite Thomas Edison for all his inventions. Admiral Rickover, sort of founder of the nuclear navy, making nuclear power into submarines. And a female scientist named Maria Mitchell from Nantucket, who really led in astronomy in her time.
If you didn't end up at your current role in the energy industry, what alternative career path would you have taken?
Yeah, so my nautical sense comes out here. Throughout all my MIT undergraduate and my graduate studies in the United Kingdom, I was planning to design racing sailboats. The Great Recession of 2008 took all the fuel out of that indulgent industry. And after a few short yacht building projects that I had, I fell back to robotics of ocean engineering and worked on some large unmanned underwater vehicles, which rely heavily on massive battery packs and the infrastructure to charge them. If I hadn't come to Idaho and the Idaho National Laboratory, I would still be working in that underwater robotics space.
And what are you most passionate about?
I guess our natural world. I love being out in nature, so enjoying, protecting, and sharing our natural world in all its beauty and power.
Well, nicely done, Tim. Appreciate it, and thanks for being a great sport and giving us the final word on this. So, like I said, we're going to give you the final word to our listeners, and what should they take away from today's conversation?
Well, as you said early on, Jason, electrification is coming. It seems inevitable. From where I sit, the automakers only keep increasing their production estimates, and everyone I talk to who buys an EV will never go back to gas. So I think it's on us to ensure that this transition is successful and sustainable, and lots of individuals have a role in that, whether you work at a utility or an automaker or are somewhere in the government, or simply promoting and talking and thinking about how you can get into an EV. That means thinking hard to find those right solutions, thinking about the realities of the electrical system that we have today and what it'll be tomorrow, and thinking differently as drivers of cars and as consumers. I am often encouraging everyone to remember that you don't own a car because you like going to the gas station. You own a car to get from here to there. Energizing that car in a different way may be more convenient, more sustainable, more cost effective, but it will certainly be different. And we need to be okay with that.
That was excellent. And no doubt that every time we have a representative from INL, we learn a ton. So and today's session obviously is no different. So thank you, Tim, for being on this call today. Thank you for joining our podcast. And we look forward to sharing your insights with us on today's episode of Power Perspectives.
Thanks again, Jason, for having me and letting me share some of what we find exciting that we're learning about EVs and how best to charge them here at the Idaho National Laboratory.
Fantastic. And we appreciate your time as well. And you can always reach Tim through the Energy Central platform, where he welcomes your questions and comments. We also want to give a shout out of thanks to the podcast sponsors that made today's episode possible. Thanks to West Monroe. West Monroe works with the nation's largest electric, gas, and water utilities in their telecommunication, grid modernization, and digital and workforce transformations. West Monroe brings a multidisciplinary team that blends utility, operations, and technology expertise to address modernizing aging infrastructure, advisory on transportation electrification, ADMS deployments, data and analytics, and cybersecurity. And once again, I'm your host, Jason Price. Plug in and stay fully charged in the discussion by hopping into the community at energycentral.com, and we'll see you next time at the Energy Central Power Perspectives podcast.